Coming up, I show how to perform a fuel ratio calibration through a mass airflow sensor tune, as well as a timing tune on a 3800 engine that happens to be swapped into a Fiero. Please thumbs up, subscribe, hit the notification bell, and I will answer any questions in the comments. This video is for educational purposes only. Tune at your own risk. Always do your own research and follow the applicable laws in your area. This video is set up in different sections that are labeled on the screen and in the description below. If you are looking to get the most out of your engine, or if you've gotten done extensively modifying your engine in any way, the first thing you're going to want to do is do a fuel ratio calibration tune using either your VE table or your mass airflow sensor. 3800s do not have a usable VE table on the factory computer setup. So instead, we're going to have to use the mass airflow sensor calibration. Your narrowband oxygen sensor can adjust the fuel about 15%, but if we get outside of this range, then we'll have to do a recalibration on the mass airflow sensor. A true tune would consist of attempting to change the air-fuel mixture that is commanded in order to optimize it for power. This is typically done around 12.5. However, the stock ECU is already pretty optimized for this when it is under wide open throttle. Calibrating the mass airflow sensor will help you to accurately command the optimal amount of fuel to air mixture. This is going to be the biggest source of power that you will ever gain from a tune. This video implies that you have a wideband O2 or oxygen sensor in your exhaust, so you can get a feedback signal on the air-fuel ratio and use that to correct your tune. For installation of that, see my previous videos on converting an older car to E85 fuel. Check out my how to swap a 3800 engine into a Fiero playlist or the build thread in the description for more information. First, we're going to have to change a bunch of parameters in order to enable us to start tuning. See the previous video about connecting to your car, downloading and writing tunes, and some basic parameters. Get out your HPTuners laptop, plug it into the HPTuners module. First, you're going to want to get the as found tune off of your car. Read the calibration on your car by pressing the read button at the top. Be sure to save a backup copy of your original tune so that we can revert back at the end. Let's change some parameters. Under engine, fuel, and cutoff or DFCO, click on the in gear cutoff, and we're going to raise the RPM limit on here before the fuel injectors cut out. The reason why is because we're going to want to tune to the highest RPM range that this engine will safely go to. Typically in any camshaft setup, your peak power RPM has been raised and you're going to need to adjust this at some point anyways. Go into Spark, Advance, and there is a RPM threshold in here. We're going to want to turn this to the same value. You won't want to go much past 6,000, maybe up to 6,500 unless you know what you're doing. Then under Fuel Temperature Control, disable this catalyst protection by maxing out this value. We will want to revert this back later if you do have a catalytic converter on your setup. But for the time being, while we are doing a calibration, we do not want this affecting the fueling. Then under Fuel Oxygen Sensors, we're going to disable closed loop completely by maxing this value out as well, because we don't want the stock O2 sensor providing feedback to the engine, causing it to command a different fuel while we are trying to tune. Because we're only going to be in open loop for the most part, you can come in here and customize exactly what fuel ratio that your car is going to try to achieve by commanding. If you are paranoid about blowing up your engine, then you can decrease this value to as low as about 11.5. Now this will be extremely rich. We're just trying to calibrate, not necessarily tune. If you're comfortable with what you're doing, you can maybe do 12 or 12.5 here. One more thing that is critical for doing this is we want to back off our timing by a little bit. This way we're going to ensure that the car is not going to knock at a high level and cause damage to your engine. Open up your timing table and just hit Control A on it and add -5 degrees. Apply this to both your high octane and your low octane tables. If you removed your balance shaft or are revving to an extremely high RPM, you might be susceptible to fake knock. Jump ahead to this section in the video for an explanation about that with spark timing tuning. Then go ahead and save this configuration. Then write the calibration to your car. Open VCM scanner and connect to the car. Now we're going to select all the parameters available in the channel list for our log. For a 3800 engine, there are not very many to pick from, so go ahead and go through pretty much all these menus and pick just about everything here. But the critical ones that you need are engine RPM, MAF frequency, mass airflow, knock, commanded air-fuel ratio, and EGR voltage if you use the EGR, or a different input that you have free on your engine if you can find one. And then go ahead and save these channels that you're monitoring. At this point, you can disconnect from the car. We're going to set up some data logging. Previous video, I installed a O2 sensor AFR gauge. Links to videos and parts in the description. I'm going to read that into HPTuners. If you don't have the pro version of HPTuners, you can unplug your EGR circuit temporarily or a different input on your computer and then read the 5-volt signal from the O2 sensors directly into the EGR input. Start by going to Tools and then MAF Parameters. Click on the first free user math option. Rename it to anything that makes sense to you, like AFR from EGR transfer. Then you're going to pretty much copy this equation. All this equation does is it converts the voltage value to the air-to-fuel ratio coming out of our fuel system from the gauge. You can click on New Variable or Edit Variable and find your EGR sensor's variable. Yours might be different depending on what your engine is because these computers could vary. Type EGR sensor into this box. One variable should pop up and you should have the units in volts. Hit OK and that is your EGR variable. If you used a different way to read in the signal, you will have to find the variable number for the signal. If instead you have the pro version of HPTuners, you can come into their pre-populated inputs and just select those as your variable instead. That's going to show up under external inputs, and whatever version of the MPVI you have, just replace what you see with what you just found. Adjust the decimals to 2. Later on, when you're connected to the car and scanning, you must adjust this offset until the gauge reading matches what HPTuners is displaying. My math said that mine should be about 9.85, but running the car actually causes slightly different voltages, and I had to reduce it down to 9.6. I want to display a gauge in HPTuners that tells me my air-to-fuel ratio, so I can see it during a log run. Right-click on the graph display and hit Gauges Layout. Remove the long-term bank 2 by clicking on them and then pressing this minus button, because we don't have that on this car. We're going to use the short-term bank 2 and change it into our AFR gauge. I'm going to turn the bank 2 to an ellipse, so I'm going to relabel it as AFR, and then we're going to scroll down and select the math from our AFR transfer function from the EGR that I set up earlier. This AFR gauge happens to read between 10 and 17 air-to-fuel ratio. I'm going to insert 7, so 7 counts between 10 and 17 by a factor of 1 with a minor tick of 5. Then we want the dials taking up a majority of the gauge, so I'm going to go between 135 degrees and 270 degrees on here. And as you can see here, the size of this thing isn't quite right, so I'm going to adjust these to adjust the position to 85% and widen it out a little bit to 16 by 25%. And I'm going to uncheck the draw minimum. Then you can hit save and save this gauge as is. So we have to make a mass airflow sensor correction equation as well. Some preset AFR ratio error equations that you can use down here, but sometimes they might not work because your car might not have these exact sensor variables. So we're going to customize our own. You can copy this equation and just replace the variables in it. Start a new math channel called MAF Error Ratio. Again, I've already made this, so I'm just going to copy this math here. You can go ahead and copy what is on the screen. Part of this equation actually uses the other equation from before. What this is doing is it is taking the error of the air-to-fuel ratio that we observe versus what we command. Then we're going to find the air-fuel ratio commanded sensor. Double-click on the variable here. At the top, just type in air-fuel ratio commanded and press yes, sounds good button. Then you can save your math equations. Now we're going to set up a table for taking and gathering data or data logging later on. Open VCM Editor. Essentially, you want to go into your airflow general and then mass airflow versus output frequency table and copy this exact table. We're going to use the feedback from the air-to-fuel ratio gauge to correct this table to do the calibration. If it's not displaying in the proper units of grams per second, then you can just right-click on it, go down to units, and change the units to what you're looking for. Yours might be different, but on this car, the mass airflow frequency in hertz is on the column axis, and on the row axis is airflow in grams per second. Go back to VCM Scanner and right-click and press Graphs Layout. Now press the Add Table button, and we're going to set up the table exactly like our mass airflow sensor table from earlier. We're just going to call it MAF Error. Make sure you have average. Now click on Parameter and type in the name of the error ratio that we set up earlier. I'm going to click on mine here, and we're going to put 5 hits required in this box. You could go maybe as low as 3, but 5 is a good solid number. That just means how many times the computer reads the value before it populates the graph with the error. Then on the column axis variable, we're going to click on the variable and type in mass airflow frequency, because again, our table from earlier had frequency on the column axis. Make sure that it is in the same units. Then we're going to go back into VCM editor and copy our column axis labels by right-clicking on the top corner of the graph. Go down to column axis and hit copy labels. Paste the labels in here. Now save your graph layout, and we're going to use this to perform our calibration and adjustment during data logging later. Open VCM scanner and connect to the car. Press the record button. Start your car and let it idle for a little while. Make sure it's well ventilated. Increase the RPM to about 2,000 and sitting in the garage. Watch the external O2 sensor value and then adjust the offset in HPTuners until you see both of them matching it. And check out what our current error ratio is. And it looks like mine is about 5% off here, which means that it is lean. You actually want it to be rich while we're tuning. So this number has got to be negative. Then press stop, disconnect from the car. So go back to VCM editor, and then we're going to multiply this entire table by 1.1 in order to bump it up 10% to try to get it rich. Then save this and write this calibration of the car real quick. You can optionally read the calibration from the car just to ensure that it wrote properly. Open VCM scanner and connect to the car. Press the record button. Now redo that test one more time by starting the car and letting it idle, and increase your RPM a little bit, and make sure that these boxes have decreased substantially. We actually want these to be slightly negative, maybe between 0 and -5%. At this point, all you're going to do is drive around a little bit in order to take some calibration data. Go into first gear so that you're not flying down the road at 100 miles an hour, and make sure that you hang out in every region of the graph for about 5 seconds or so. Drive up to your RPM limit. Try not to go over about 6,500 on these engines unless you know what you're doing. Hit the stop recording and save this data log. Disconnect from the car. Now after you've taken your data, so copy this table by right-clicking and press copy, and then go back into VCM editor and right-click on our chart and paste the table. And you can do multiply by percent. That will very quickly adjust this, but typically that might overshoot a little bit. So why don't you hit multiply by half if you're not comfortable with that. Make sure that once you paste this data, you can click the split view in order to see a graph of this screen. Then you can smooth out this curve here. If you see any spikes in this curve, then it's probably not right. And what you can do is you can highlight the cells that have a spike in them and the several around it, and then click on the smooth horizontal button to smooth out this curve. Now you're probably not going to get into the highest range that this mass airflow sensor is capable of unless you have a crazy setup like me. And then just redo this calibration 3 or 4 times. Rewrite this calibration, reread this calibration, and repeat. Continue to smooth out until the error ratio is only about 1% off or less in each box. In order to revert all the settings that we changed in the tune, we're going to open up the original backup by going to Open Compare File. This way, any differences between these two tunes will be highlighted in green, and we can just change it back by copying and pasting. Readjust your open loop air-to-fuel ratio back to stock numbers. Change your DFCO back. And with that, change your Spark Advance limitation RPM threshold back to stock unless you have a camshaft that can support a higher RPM. Re-enable your catalyst protection, disable closed loop all the time, and then put some timing back into your timing table. Open up your timing table and just hit Control A on it and add 5 degrees. Change your low octane table back to the stock numbers. Make sure you plug back your EGR, and that concludes our fuel tuning. Now you can easily tune timing. You have to do fuel before you do the timing tune. What we're going to do is rely on our knock sensors to tell us when we have advanced our timing too much and are starting to knock. Knocking, or pre-detonation, could be your fuel exploding in an uncontrolled manner because your cylinder is getting too hot. This could result in very deadly damage to your engine. Check out my Everything There Is to Know About a 3800 video for some more information about knocking and fuel. As a rule of thumb on an engine, typically your ideal peak power that you can achieve through tuning your timing is going to be achieved by several degrees before your knock sensors start detecting knock. However, right before you start to knock, your peak power curve actually drops off a little bit. So we're going to find where the engine starts knocking and then back it off. This could be dangerous to your engine. Do not run high sustained knocking. If you see a spark reduction of 5 degrees here consistently, you want to immediately stop and back off your table by twice that amount of timing. The only way to truly tell without a dyno tune if you've picked up power is under the same exact conditions if your car goes faster at the drag strip. Or you can take a data log and see how fast you can accelerate to a certain speed and then repeat after you've made your timing changes later. And if you've improved in acceleration, then you've also picked up some horsepower. There is an issue where stock knock sensors are very sensitive, and if you are running the engine outside of a stock RPM range, they will start reporting knock when they actually don't see any knock, and we call that fake knock. This might occur if you've deleted your balance shaft or if you're revving your engine higher than normal. The way that you tell if you have fake knock is if you start to get knocking and timing reduction, then what you can do is back it off by say 10 degrees and rerun. And if you continue to get timing reduction in that same area, then that is definitely not knocking, it is fake knock. At that point, you're going to have to go and get a professional dyno tune in order to find your actual peak power curve, instead of guess with finding where knocking is and backing it off a few degrees. So alternatively, instead you can completely disable the spark knock sensors by just unplugging them and running without them. However, this obviously will not protect your engine. Start by going to Engine, Spark, Advance, and High Octane, and copy this table to your low octane table. This way, if you get some sort of knock, it will not change based on that. In a high performance application, you might just want to leave the stock high octane table in the low octane table. Now go to Spark, Advanced, and Fuel Base, and we're going to remove any spark adders in here so that they don't affect our tune while we're trying to calibrate it. And also zero out the intake air temperature Spark Advanced table as well. In a high performance application, you may want to just leave these tables zeroed out, but you need to do your own research. You can probably zero out your engine coolant temperature table here too, but I did not. Then go ahead and save this configuration. Then write the calibration to your car. And we're going to set up a timing table exactly like what we just did for our mass airflow sensor calibration. Under Spark, Advance, and then high octane or low octane, doesn't matter. Find your Spark Advanced base table, and we're going to copy this exact table in here. On this engine, it is cylinder air mass in grams versus engine speed or RPM. Go back over to VCM Scanner and go to your graphs and right click and hit graphs layout again. Let's create a new graph by pressing the plus button, and let's call this the Spark timing table. Now we're going to click on the variable to use, and we're going to use this one called Spark reduction in degrees. Now I want to do some color scales on this graph. I'm going to do a high value of 10 degrees at red and a low value of 0 degrees at green. The middle value of 5. And this one is a little bit trickier, but mine is called MAF cylinder air mass, and I'm going to click on the 6-cylinder one here, and the unit is going to be in grams. And now I'm going to copy the column axis labels into this column labels on the chart. Then for our second parameter here, we're going to type in engine speed or RPM because that's the row axis on my other chart. And we're going to go in the other chart and copy the row axis labels now and paste them into this chart. Adjust the amount of hits. You can be a little bit more aggressive here. You can do maybe 3 or 5. You could also do the maximum value just in case, but I'm going to leave mine as average. Open VCM Scanner and connect to the car. Press the record button. You just take this thing for a drive again, and again, try to shift it into first gear and get into every RPM range that you possibly can. You're going to want to get into wide open throttle for your timing quite a bit too. You might want to go through a few different gears here to get a wider range of different data collected. Hit the stop recording and save this data log. Disconnect from the car. If you don't have any knock at all, then you can start increasing your timing table, or at least some regions of it, by say 2 degrees at a time. Rewrite this calibration, reread this calibration, do some more data logging, and check to see if you've reached any knock. Repeat this process until your engine actually does start to exhibit some knocking. As you see here, there has been some spark reductions. Then what you're going to do is back off by 2 to 5 degrees, maybe a little bit more on this to be on the safe side, and that should be close to around where your peak power should be being produced. Keep in mind that air temperatures can change on a daily basis. You might want to monitor your knocking on different temperature days. Higher temperature days are going to result in more knocking because of hotter combustion. Then last, we're going to undo our changes. In a high performance application, you might just want to leave the stock high octane table in the low octane table, and then save and then write the calibration. With those two things considered, your car should be properly calibrated and tuned for close to optimal power and performance. Shout out to T Meister for joining the shout out level on the channel. Thank you for your support. If you'd like to sign up for channel membership for various benefits, click the join button on this video. See how you can continue to support what I'm doing with the links in the description. That's it for this video. Please give it a thumbs up, subscribe, hit the notifications, and I will answer any questions in the comments.